Welcome to this explainer, everyone. Look, if you're working in the Internet of Things, you already know the real headache isn't collecting data. Honestly, we're practically drowning in it, right? The actual challenge, the real heavy lifting, is taking all that invisible machine data and translating it into clear, actionable human stories. Today, we're diving into Chapter 8 of our source material, all about visualization and techniques, and we're going to see exactly how to build what the text calls the prism of insight. Because think about it. Machine language, it's just relentless, highly structured, completely invisible JSON logs. To a computer, yeah, that's absolutely perfect. But to a human operator who's just trying to figure out if, say, a server room is overheating, it is completely useless. But the second we translate that into a simple line chart, boom, we immediately see shapes, patterns, a sudden spike in temperature. Data visualization isn't just about making things look pretty. It's literally the essential translation layer between a machine's reality and our human understanding. So to get us from that giant wall of text to actual, clear insight, we'll be following a systematic 3-step methodology outlined in the chapter today. Section 1 covers understanding information, Section 2 is the selection of techniques, and Section 3 is implementation. Okay, let's jump right into Step 1, understanding information. Because honestly, before we even think about drawing a single chart, we have to interrogate the raw material. Think of your IoT sensors as capturing this incredibly messy, unstructured reality. The text points out that our first job is to funnel that absolute chaos into structured data frames. Basically, picture a massive spreadsheet where your rows are individual time records and the columns are your specific sensors. But we don't just stop there. Next, we use descriptive statistics, specifically hunting for the mathematical center and the spread, which are represented by the Greek letters mu and sigma. You see, only after we find the mathematical shape can we actually render the visual shape. Now, when we talk about finding that mathematical shape, we're really comparing two core statistical pillars. On one side, you've got central tendency, so your mean, median, and mode. This essentially asks the question, where does the typical sensor reading sit? And then on the other side, we have variability, variance, standard deviation, range, and interquartile range. This one asks how much noise or fluctuation is actually happening in this physical environment. You absolutely need both of these to tell the true story. And what's really fascinating here is how these seemingly abstract numbers actually ground us in physical reality. Statistics aren't just dry math. They quite literally define the physical boundaries of your IoT environment. The mean, it acts as your anchor. But the standard deviation is arguably even more crucial because it defines the expected operational zone of that physical space. Basically, as long as the data stays within that spread, you know the machine is behaving normally. Which brings us perfectly to the concept of the outlier. When you see a data point suddenly shooting way outside that expected operational zone, it isn't just some statistical quirk. No, in the world of IoT, an outlier very often translates directly to a real-world hardware failure, maybe a security breach, or some critical physical event that demands immediate human attention. In fact, finding those outliers is often the entire point of the system. All right, moving right along to Step 2, selection of techniques. So now that we understand our data mathematically, how do we actually choose the right visual lens? Here is the absolute golden rule you need to remember. Never, ever choose a chart just because it looks cool. Choose it based on the specific data relationship you need to reveal. Ask yourself, what is the intent of your communication? Are you trying to show how a sensor changes over time? Are you trying to spot anomalies? Maybe see if two sensors are impacting each other. Your intent has to dictate the visual. You can really think of this mapping as your practical translation rulebook. Say your goal is tracking a trend over time, like temperature over a 24-hour period, while your technique is the line plot, right? You want that continuous connected line. If you need to look at the distribution of data to sniff out noise or anomalies, you're going to use a histogram or a box plot to visualize the density. Or for correlation, say you're comparing humidity against temperature to see if they influence each other, you'd use a scatter plot to look at those dispersed dots. It's all about matching the specific engineering goal to its exact visual signature. Let's zoom in on one specific and honestly incredibly powerful technique, the box plot. A standard histogram is fantastic for showing distribution, but let's face it, it eats up a lot of screen real estate. A box plot, on the other hand, is essentially a top-down view of that exact same histogram. It condenses the whole shebang, the median, the interquartile range, and, crucially, the outliers, into a single horizontal line. Why is this such a game changer? Well, in IoT, you rarely ever have just one sensor. The box plot lets an engineer stack dozens of sensors side by side on a single dashboard so you can spot the anomalous machine instantly. And that brings us to our final step, step 3, implementation. Let's actually look at how we build this translation prism using code. So let's see how this all builds upon the Python visualization stack. Down at the base, you've got your data engine. That's NumPy and Pandas handling the arrays, the data frames, and all the messy cleaning. Above that sits the foundation, Matplotlib. This is your low-level API giving you super granular control over literally every single pixel and access. And then, sitting right at the very top is the facade, Seaborn. Seaborn is built directly on top of Matplotlib, but it gives you a much higher-level API, really concise syntax, and just beautiful default themes. This means you can focus on statistical elegance rather than, stressing over coding individual tick marks. The relationship between the code you write and the visual output you get is beautifully direct. Simple syntax maps perfectly to those visual signatures we talked about. Just calling sns.set_theme instantly gives you a really clean, dark grid. Then calling sns.scatterplot and just assigning your x and y variables directly renders those dispersed blue dots showing the correlation between temperature and humidity. I mean, the code is literally drawing your physical relationships right there on the screen. If you want to package all of this up into a repeatable engineering pipeline, it basically looks exactly like this 4-step process. Step 1, acquire and load your dirty logs using read_CSV. Step 2, clean and impute. So handling those annoying missing sensor drops with commands like drop in A or fill in A. Step 3, group and aggregate. This takes you beyond just raw logs to actual insights by grouping data, maybe by room ID. And finally, step 4, visualize. This is where you deploy Matplotlib or Seaborn with a quick plt.show to finally render the shape of your reality. So, bringing it all back together, this is your ultimate translation prism. First, you understand the mathematical boundaries using pandas and descriptive statistics. Next, you select your charts incredibly strategically, based purely on the relationship you need to reveal. And finally, you implement the whole thing using Matplotlib for that granular control and Seaborn for the statistical elegance. I want to leave you with a final, really provocative thought from our source material today. Look, our systems are incredibly good at hoarding numbers, but numbers alone don't solve problems. Human beings solve problems. The ultimate goal of this methodology isn't just to make pretty charts for the sake of it. It's to make the invisible visible. Stop just collecting data and start communicating insight. Thanks for joining me on this explainer, and I'll catch you next time.